In this video, we're going to have a look at how to change your tree more carefully. So far we've used insert before, we've used add, we've used some of these slots that allows us to modify our tree. Because if the task of the Magic's Hyperlambda runtime is to modify an existing piece of Hyperlambda code, then the question obviously becomes, okay, what capabilities do we have in regards to actually modifying our tree? So open up tools, open up MISC, open up the evaluator, and let's write some Hyperlambda. Let's write dot data to have a data segment. Let's write foo1, bar1, foo2, bar2, foo3, bar3. And that's our data, that's our data segment. Now we're going to manipulate one of these nodes. So let's change its value. Set dash value. Yet again, you can do control space on Windows or function control space on Mac to get autocomplete. Colon x colon at dot data slash asterisk slash foo2 and then dot colon how the dash word. If you execute this code, you see we just changed the value of the foo2 node from bar2 to becoming how the word. If we change from foo2 to foo3 here now, you will see that we changed the value of the foo3 node. This is the set value. Now I want to emphasize that most of these nodes can actually modify multiple nodes at the same time. So if I invoke this without its slash foo3 parts of the expression, then it actually changes every single node. Why? Because the expression is returning multiple nodes. And most of these slots that allows you to modify or retrieve or whatever on particular node resulting sets allows you to modify multiple values at the same time. So if you can see up here, we have bar1, bar2, bar3, and at the bottom here, we have howdy world, howdy world, howdy world. So we modified multiple node values at the same time. That's how the set value works. Now, obviously, there's a set name. If you execute set name now, we no longer change the value, but we actually change the name of the node. Now we had the same static value, so now the name became how they were instead of the value. Then we have the add node. Now at this point we're going to have to slightly modify our code here and do, for instance, how the dash world, for instance, world. For instance, and if you execute this, you see that it actually adds into every single node that results of this particular expression, this particular node set. And of course, if we want to, as we showed in a previous video, we had source, howdy, colon world. We can also do a get nodes here, and let's create multiple nodes here just for fun. Howdy 2, world 2, and then at the bottom here, instead of having this static code, let's do get dash nodes colon x colon at dot source slash asterisk. If you now execute this code, you will see it evaluates the expression leading to howdy 1 and howdy 2 as part of the get nodes invocation down here, and then it adds it into the result of this particular expression, which leads to, of course, every single node here. So every one of these nodes will have two additional children nodes, being howdy 1 and howdy 2. And if we browse down here, we will see howdy 1, howdy 2, howdy 1, howdy 2, howdy 1, howdy 2. So now let's check out the difference between add and insert before and insert after, because they're basically the exact same. So let me write insert dash before colon x colon at dot data slash asterisk slash foo2. This points to, of course, obviously this node. If I now do tab dot catch return tab howdy dash world and I execute this particular code, then if you carefully watch the foo2 node here, now you will see that foo2 node now all of a sudden has a node before it, being the howdy world node, which is this node that we added as the source for our insert before invocation. If we change it to insert after, if you watch carefully here now, watch the position at line 6 here, there's this howdy world node. If we execute it again, it's actually below the foo2 node. Why? Because obviously insert after means insert after and insert before means insert before, right? So now we have the ability to set a value, we have the ability to set a name, we have the ability to add nodes, which basically means append into the children collection node of the particular node, resulting in the expression given to the add invocation. We have the ability to change the value, and we have the ability to change the name of a node. Basically, we have every single axiom that is required in order to perform CRUD on our code. So far, we have used these expressions, but we haven't really gone deeply into them and analyzed them. So let's do just that, right? So as we spoke about in our first video, this at thing basically means find the first node whose name is .data, right? Then we have another one called /*, then we have another one called /foo. Now, what are these things? These are three different iterators. You see, an expression is built by iterators, and each iterator is separated by a slash. So this means that this is an iterator, this is an iterator, and this is an iterator. This iterator, as we spoke about previously, finds the first node whose name happens to be .data upwards in the hierarchy, implying if we do .data like this, then actually this will not find this data node, but it will actually find this data node. Why? Because it only goes upwards in the hierarchy, and in order to find this one, it has to go up and then in, right? So this one here will not result in finding this. And in fact, you can actually test it by executing the code if you wish to, if you have this particular code. So, sorry. Now you see it still finds this data node and not this one. Now, then we have another iterator, and this is the asterisk iterator. And it basically means give me all the children of whatever you got previously. Now, if I does like this, dot, and then slash, then it will find children. This dot iterator means give me the root node. Remember, we spoke about the root node being the invisible node, whose all of the first level nodes are children of this invisible node being the root node. This basically means give me the children of every single root node. Now, this is probably going to result in some sort of like logical error. Why? Because it tries to insert stuff into, among other things, the insert after thing too, right? However, we could, I guess, actually make it work by doing 0, comma 2 inside of 2 square brackets. So let me just sanity check this code before I actually execute it. So it finds the root node, then it finds all of the root node's children, returning source, data, and insert after. Then it returns a subset of those nodes, being the 0th node and the first node, which basically is this node and this node. And then asterisk, and actually let's keep it there. Then it finds all of those nodes children, which implies basically how they were 2 were, and foo1 and foo2 and foo3. Now, obviously, this is going to result in a slightly funny result set, but I actually think it actually is going to work. And as you can see here, it invoked insert after on how the 1, on how the 2, foo1, foo2, and foo3. And basically, we ended up getting like 5 new nodes in our tree. So how many different iterators does there exist? Well, there exists a bunch of iterators actually, but for all practical concerns, I mean, you will be using a handful of these iterators. You might be using the root iterator, you might be using the children iterator, maybe you might be using the all descendants iterator, but actually quite rarely, you might be using the named iterator. If I do .data /* now, then it actually filters on nodes whose name is .data, because this is the default iterator it's using unless it can find a more specific match for an iterator. So .data here basically implies give me everything whose name is data. If I have multiple data segments here, .data, and then foo1, actually let me just copy it for simplicity reasons, and then I execute it, then you will see both of my .data segments are actually given a match. Why? Because they're both having the name of .data. And since this is a named iterator filtering type of iterator, it will actually filter away everything whose name is not data, implying it will get a match for both of my .data nodes. And then again, it will return the children of all of those. This allows you to actually do what is referred to in mathematics as graph object hyperplane. So you basically create a new graph object as a hyperplane of your previous graph object. Now, if you're interested in every single iterator that exists, or you're interested in reading more about insert after, add, or insert before, or set name, or set dash value, then the simplest way to find that is actually to collapse this guy, click the documentation, make sure you have pop-up blockers turned off, scroll to the bottom, find docs, and click the magic.node and or the magic lambda. Now the magic node documentation here, this is the reference documentation for magic. You see, magic isn't one project, it's actually almost 40 projects, and they're loosely coupled together using this sign pattern called signals and slots or active events, or depending upon what version you read about it in. If I click on magic node here, for instance, I see the reference documentation for the project called magic node, and the project called magic node happens to be containing the lambda expressions part. So if I now, go down here and I find the lambda expressions in the magic.node documentation, I can actually read about iterators in details, and I can see a complete list of every single iterator that exists. This one is probably the most weird one, and it's almost exclusively only used when you're doing for each loops. This one is the minus iterator. We have actually used the minus iterator a couple of times, and it basically means give me my older sibling, or the sibling upwards in the hierarchy. This one goes the other way, so it means give me my older sibling. This one means give me my parent node. This one means give me the root node of whatever graph object I currently happen to be executing. This means give me every single descendants of my previous node result sets. And then comes the kicker, the extrapolated expressions. We will go into that a little bit in 1 minute. However, let's just finish all the iterators. Equality iterator. Let's show the quality iterator because it's actually kind of interesting. So now, hooray! Now let's open up MISC again, evaluator, and then let's do dot data foo1 bar1. foo2 bar2, foo3 bar3, and then let's do a set dash value colon x colon at dot data slash asterisk slash equal bar2 dot howdy world. What do you think is going to be the result of this? You probably guessed it already. Why? Because the equality iterator basically checks the value of the node instead of its name. Let's see, I probably lost myself completely here. Here we have the subset of the previous result set. It's basically a from and to array type of filtering condition. Then we have the at xxx node. We've seen that one. Then we have the numbered iterator. And in fact, if I do now, instead of I do bar2, let's do 2, the number 2. You see, if whatever you're supplying as a name filtering iterator happens to be a number, then it will actually by default believe that you're not interested in the name of the node, but you're actually looking for the second chart, and of course it's a 0-based array. So this is 0, 1, and second. So here you can see foo3 gets howdy world. If you change it to 1, it's foo2 that gets howdy world. And then we have the extrapolated expression, which is a fairly complex subject, and you'd probably never have to actually use it in your own code, but it's there in Magic for those rare cases when you simply need it. So let's show how it works by doing asterisk slash, and then let's create an extrapolated expression dot src dash node. Let's now create a node whose name is src node. Make sure you add an at before here, and then let's do foo2. Now you will see that what it actually does, it evaluates this first as an expression. So this is a nested expression inside of our expression, or an extrapolated expression if you wish. Now this expression of course leads to source node. source node happens to have a value of foo2, so the entirety of this thing here is now substituted with foo2, meaning it becomes like dot data, all of its children, then foo2. And this allows you to parameterize expressions as you see fit. Now there's a lot more to expressions, and there's a lot more to set value and set name and add and insert before and insert after, etc., etc. If you want to look at the documentation for add, insert, before, insert after, etc., etc., you want to check out Magic Lambda. So there are two projects you want to check out related to expressions and modifying your tree. It is the magic.node project, and then there's the Magic Lambda project. And the Magic Lambda project is arguably the closest you come to the programming language keywords in Magic. And here you can scroll down, and if you look for square brackets add, for instance, you will find the documentation for add here. If you look for instance, for square brackets set dash name, you will find the documentation for set name. I want to say one thing, which is that you don't need to have static values here. Now I have a node up here that says source node, right? If I want to, I can do stuff such as get dash value, colon x colon, at dot source dash node. Let's hope this works. And it actually did. So now you see my expression. Let's make our expression slightly simpler. Foo2 to avoid mixing up constructs. So here we have an expression saying dot data, all of its children, foo2, pointing obviously to this guy. Then we have an expression given to get value here that points to its the dot source node, of course having a value of foo2, and actually let's change it to Thomas Hansen, because then it becomes more easily observed down here, and then it changes it to Thomas Hansen. And of course, for the record, there is a get name equivalent to the get value to